Hi everyone, this is video number 2 for the Unit 13, Aromaticity. I know that for our first video, I threw a lot at you, and we introduced aromaticity, or aromatic molecules, and we saw that benzene was especially stable when we took a look at its reactivity. So before we delve too deeply into what exactly aromaticity is, or aromatic stabilization is, let me look or summarize what we did in video 1. Because in video 1, we focus on the molecule benzene, and we saw that it's stable. Why? Because it didn't react with Br2, uh, whereas cyclobutadiene, right, versus this molecule is pretty reactive. Okay. We also saw that the bond lengths are all identical. And we could consider that, or we can attribute that to resonance. Whereas cyclobutadiene does not undergo resonance, and the CC bonds are different, right? The carbon-carbon double bond is 1.3 angstroms, while the single bond is 1.5 angstroms. But for benzene, all carbon-carbon bonds are 1.4 angstroms. And we can attribute that to resonance. But I am trying to draw a line, which I have not done yet, between aromatic stabilization and resonance stabilization. Okay. And that's the issue for this unit, or for this video. Before we do that, one more thing in video 1. We saw 3 categories. We could categorize the molecules aromatic, anti-aromatic, or non-aromatic. Okay. I'm not going to go over those rules. That's in video 1, and we'll practice here and other videos. But I do want to mention that aromatic molecules are the most stable. Okay. Followed by what? Non-aromatic. I might have discussed or mentioned non-aromatic as being agnostic. It has nothing to do with aromaticity or anti-aromaticity. Okay. Anti-aromaticity actually makes a molecule less stable. It not only does it not stabilize the molecule, it actually makes it less stable than what you would expect. Okay, so this is anti-aromatic. We will do examples, maybe not in this video, but in the next video, to categorize these molecules into these 3 buckets. Okay, let me talk about a couple more experiments that sort of point to the idea that aromaticity is different than resonance, and also how do we visualize aromaticity using what's called a frost circle. So the first piece of evidence is going to be the heats of hydrogenation, or hydrogenation, sorry. If we have an energy diagram, we've seen this before, the higher up the vertical axis, the more unstable the molecule is. And when we talk about alkenes, when we hydrogenate alkenes, we typically lower the energy. Or you could even think of it as release energy, right? So here, if we hydrogenate cyclohexene to cyclohexane, we're going to release energy, and the resulting molecule is much lower in energy. And that amount of energy actually is measurable, and it's 120 kilojoules per mole. So how do I want to draw this? From this level down to this level. Okay, 120 kilojoules per mole. Okay, I did not give myself a lot of room, unfortunately. Theoretically, if we have benzene way up here, and each of those double bonds hydrogenates and releases 120 kilojoules per mole of energy, then you would predict that doing this hydrogenation, right, would be 360, theoretically. So this is 360, but it's theoretical. That just comes from 120 times 3. But in actuality, benzene is much lower in energy than the theoretical benzene, or you could even think of this as cyclohexatriene. Benzene is lower. And again, this is not to scale, unfortunately, but also all of these should be on the same level. Okay. Actually, it only releases 210. So release 210 kilojoules per mole. So there was some stabilization taking place, right, between these two levels here. You could call this the stabilization energy. So that's the difference between the theoretical and the actual. Okay, sorry, I keep turning this. Actually releases 210 kilojoules per mole. What's the difference? That's 150, right? 150 kilojoules per mole of stabilization. I'm not going to show you the numbers, but the stabilization due to resonance to conjugation would not equal this much. So there has to be some other type of stabilization added on top of resonance and conjugation. So that's actually a very important point, that conjugation and resonance does not account for all 150 kilojoules per mole of stabilization. Okay, so that's one set of data using the experiment heats of hydrogenation. We're hydrogenating all of these. This was theoretical, but when we hydrogenate this molecule, again, it's going to be under kind of extreme conditions, but it doesn't change the fact that you're ending up in the same place and you're releasing that amount of energy to get to the same place. I think you could have like high pressure, high temperature, etc. Maybe a different catalyst. I don't know. I'm not sure what catalyst. I could look that up later, but extreme conditions to get this to hydrogenate. All right, so that number, it's not important to memorize, but it's important to understand that this is a combination of resonance stabilization, which goes hand in hand with conjugation stabilization, and something else. And that something else is called um, aromaticity or aromatic stabilization. Stabilization. Sorry about the spelling. Let me give you another example. That example is going to use the stop sign. If I could find it. Here it is. So with benzene, we say that, let me find it real quick. Let me just double check my numbers. Yeah, I'm okay. I'm good with these numbers. Um, okay. For benzene, the heat of hydrogenation, meaning the heat released upon hydrogenation, we said was equal to 210 kilojoules per mole. And this is considered much lower than the theoretical 360. Yeah. But what about the stop sign? Cyclotetra, cyclooctatetrene, octatetrene, 4 double bonds, octatetrene. What would be the theoretical for this one? It would be 120 kilojoules per mole times 4. The heat of hydrogenation is lower, and that equals 410. That's really not that much lower than our theoretical, what was it, 480. Not as low as we would expect. Okay, this is only a difference of 70 kilojoules per mole. This is a difference of 150 kilojoules per mole. So even though we can visualize stabilization due to resonance, right, just by, well, I'm not going to draw that, but you know your mechanism errors for resonance. Cyclooctatetrene does not benefit from that, does not benefit from the possibility of resonance here. So this is surprising. It's not stabilized, or not as stabilized. And this is actually not aromatic. So our terminology is going to be super important because my choices are aromatic, non-aromatic, or anti-aromatic. When I say not aromatic, that only tells me that it's one of these two, right? So let me use more specific language, and I'm going to say, and I haven't explained why just yet, cyclooctatetrene is non-aromatic. Now, those of you who were really paying attention to that first video, I know what you're doing. You're looking at those rules of aromaticity, right? And you're counting up the pi electrons. You know, if we look back at those rules, right, we have 8 pi electrons. So it doesn't fit the Huckel number. So many of you are thinking, well, yeah, all the atoms are sp2. The molecule, the way I drew it, is flat, but it doesn't follow rule number 3. I should be anti-aromatic. The thing is, and I know I'm jumping around a bit, the thing is, anti-aromatic is so destabilizing that if a molecule can conform in such a way that it becomes non-aromatic, then yes, that molecule will jump from being anti-aromatic to non-aromatic. You know how cyclooctatetrene does that? It says, I don't want to be anti-aromatic, so let me violate rule number 2, and that way I become neither aromatic or anti-aromatic, right? Anti-aromatic still has to follow rule number 2, but now I am non-aromatic. And that is actually better than being anti-aromatic. Okay. let me summarize that, and then we'll come back to these examples. So, as we go through the videos, what we're doing is we're building up a repertoire of uh, all these different examples and what category they fit into. All right, we know that this is aromatic. Now that we know that this is non-aromatic, that's because it conforms to be not flat. Because if it was flat, and the fact that you have 8 pi electrons, that molecule would be anti-aromatic, which is very destabilizing. So instead, it's kind of hard to see in 3 dimensions, but that stop sign can look like this. And you would have your double bonds where alternating, right? Like this. Almost like a boat, sometimes people call it, but it puckers, it unflattens, so we can't have resonance because now our p orbitals are not aligned. Now, normally you would think, oh, wow, I really don't want my p orbitals aligned. I really want to avoid resonance. You want to avoid resonance because if you have resonance, your molecule is flat, and now you're back to being anti-aromatic. It's kind of it's a difficult path to follow um, if you don't really understand your rules of aromaticity. Okay, and knowing that a molecule just by twisting, right? Molecules are dynamic. The molecule is actually more stable, which is interesting. It's more stable in this conformation. This conformation. Why is that surprising? More stable without resonance, without being flat. Okay. That's sort of indirect evidence that these molecules that are aromatic, they're not dependent. Well, I shouldn't say dependent, but it's it's a different phenomenon than resonance. Because if resonance really was the stabilizing force, then that molecule will become flat to show resonance. But there's some other force preventing it from showing resonance, and that is the idea that it can't be or doesn't want to be anti-aromatic. Don't worry, we will do plenty of examples. Um, but now is when I'm going to show you why Huckel's number is important, okay, in terms of determining this idea of aromaticity. You recall that when we did hybridization, right, when we have like an sp3 carbon, mathematically, what did you do? Mathematically, you took these wave functions that describe the 4 atomic orbitals, s plus p plus p plus p. Here we have 4 atomic orbitals. Then we did hybridization. And do you remember what the rule was? If you combine 4 atomic orbitals, you should have 4 hybrid orbitals. And yes, they're all called sp3, but we should have 4 of them. That's why carbon, when everything's singly bonded around it, is tetrahedral. 4 hybrid orbitals. For benzene, we're not going to be looking at hybrid orbitals. Okay, I know that we have that these are sp2 hybridized, but what I'm more concerned about is not the hybrid orbitals, but the p orbitals. How many p orbitals do we have for benzene? We have definitely 6 pi electrons, right? And those pi electrons are pi electrons because they participate in making these pi bonds. So my conclusion here is that I have 6 p orbitals to contain what? The 6, or to hold the 6 pi electrons. Okay. What am I setting you up for? I'm setting you up to conserve the number of orbitals, because these are 6p atomic orbitals. Another way that you can think about combining orbitals is, can you make an orbital that encompasses the whole molecule? Can you make an orbital that describes the electrons, not just for each of these atoms separately, but describes where that electron can exist in terms of the whole molecule? This is a new concept for many of us. These are called molecular orbitals, or MOs, and you should have 6 of them. So if you combine these p orbitals, you should have 6 molecular orbitals, and they're abbreviated MOs. Now, I typically don't go through a lot of MO theory in my class, at least for Organic 1 and Organic 2. I save that for um, advanced organic or physical organic chemistry. But just like we were able to show the energy levels for our hybrid orbitals, right? These are all on the same orbital, same energy level, okay? We could do the same thing for the 6 molecular orbitals. Just remember this: 6p orbitals, 6 molecular orbitals, okay? For instance, for cyclobutadiene, you have 2 pi bonds, so you have 4p orbitals. Is that true? Like this, right? sp2, 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 sp2. So this would have 4 molecular orbitals. And specifically, these are pi molecular orbitals. I should definitely say that. Okay, so don't worry about this. I wrote this down because we know that there are 4 pi MOs because there are 4 p orbitals. Okay, that's just an aside. All right, so here is the deal. What are the energy levels of those 6 molecular orbitals? They're actually arranged like this. Scientists have figured this out mathematically and backed it up with experiments, but your MOs look like that, and they're labeled. You could call this maybe pi 1, pi 2, pi 3. Okay, we'll label them. Pi 1, pi 2, pi 3, pi 4, pi 5, pi 6. Do you recall that, like when we did hybrid orbitals, we could still have orbitals and they still exist even though they're not occupied? A classic case is a carbocation. We know that there's a p orbital for carbocation, but it's empty, but it still exists. Same thing here, because what we have to worry about now is that we have 6 pi electrons. So we're still using the rules that we've learned way back in general chemistry, that you doubly fill each orbital, or the maximum number of electrons you could fill in each orbital is 2, and you singly fill each orbital that is the same energy before you doubly fill them. 1, 2, 3, 4, 5, 6. Okay. We have a midpoint. I know this is very abstract. It is abstract because a lot of simplification has to be done, or else we'd be bogged down in wave equations and math. I'm trying to distill this to what you need to know. So this is called the non-bonding line, the midpoint. And everything below it is considered a bonding orbital. Everything above it is called an anti-bonding orbital. And normally the anti-bonding orbital would have a star. So pi 4 star or pi star 4, pi 6 star, pi 5 star. These orbitals exist. They are in the molecule, but they're not occupied. We know that they exist because when you excite electrons by pulsing them with energy, that electron will jump to the next higher energy level. And it has to jump somewhere, and it jumps into these other MOs. I'm not showing you visually what these MOs look like. Like, I'm showing you visually how the p orbitals look like. But the, to really get an appreciation of what a molecule is, you really should, in higher level chemistry, understand what the molecular orbitals look like, because now you're treating the molecule as a whole. You're not trying to have, put pieces together and try to construct a molecule or molecular orbital from its individual pieces. Mathematically, you could do this and you get kind of weird looking shapes, okay? Shapes that we're not going to be concerned with. What I am concerned with is this is why Huckel's number is important, because every electron is paired and every electron is in a bonding orbital. That's aromaticity. Aromatic, when you have every pi electron paired, and I just want to double check this. I think every pi electron is in bonding MO, okay, not atomic orbital, but molecular orbital. This is memorization, okay, the way that MO energy levels are arranged. Let's take our classical anti-aromatic molecule. Now we know this is anti-aromatic because it follows rule 1 and 2 from the last video, right? It's all sp2. It's relatively flat. Okay, I know you could pucker a square, but it's flat enough that we're going to consider it flat. It cannot do what cyclooctatetrene can do. It cannot form a boat. So this is anti-aromatic. But how do I show that with MOs? Okay, we're going to use what's called a frost circle. The frost circle for benzene looks like this. Okay. You're going to try to encapsulate your polygon in a circle. Okay, and wherever it touches the circle, that's an energy level. What is this? This is like a mnemonic. It's not really based off of any physical characteristic of the molecule. It's just that it turns out when you run these calculations, when you add all of these p orbitals, the mathematical equations for these, you get the energy levels like such. Okay, and again for benzene, 1, 2, 3, 4, 5, 6, and you have your non-bonding line. What do you do for a 4-membered ring? Okay, let me see if I could do this a little bit better. It doesn't matter if it's smaller or bigger, but let me do this. The rule is for a polygon, for a cyclic molecule that you may think is aromatic, you have to have one point at the bottom. So I'm going to tilt it so it looks like a diamond. Now, yes, this is your non-bonding line. And where are your energy levels? Your energy levels are here, 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 and here. Pi 1, pi 2, pi 3, pi 4. This is pi 4 star. This is pi 1. Now the non-bonding are neither bonding or anti-bonding. Okay, so we'll just call it pi 2 and pi 3. 4 pi electrons though. See, it's important that we know how to count pi electrons. 1, 2, 3, 4. This is not a good situation because unpaired electrons, and this is again something that you should memorize. Okay, we're not going to get into the the physical chemistry of why this is the case, not in organic, but unpaired electrons are very unstable. And hence, that's why Huggle's number is important, because this is 4 pi electrons. In practice, we're not going to be doing a lot of frost circles. This is just one very simplistic way to show you, oh, this is aromaticity, and this is anti-aromaticity. This is where stability, the extra stability, comes from. It really has nothing to do directly with resonance. Okay, it has to deal with where those electrons are on an MO diagram. Okay, so this is now anti-aromatic. Okay, we could show it by cartoon or by frost circle, but really it's anti-aromatic because of our rules that we went over in video 1. It is flat. That's actually rule number 2. It has all sp2 carbons or sp2 atoms. It doesn't have to be carbon. But now I have 4 pi electrons, not 2, 6, 10, 14, etc. That's anti-aromatic. If you're following and you were building up our categories, we have one molecule per category now. Okay. We have benzene, we have cyclobutadiene, and then we have cyclooctatetrene. From here on out, well, for the next video, we're going to look at more examples, and we're going to build up our ability to determine whether a molecule is aromatic, non-aromatic, or anti-aromatic. And then in the video after that, we're going to see how aromaticity helps us predict not only reactivity, but some really cool problems where we could predict that, oh, due to aromaticity, this molecule is more basic than the other, or this molecule is more acidic than another. And that will be based off of aromaticity now. Because it's a stabilization effect, we could look at the stability of the conjugate acids and conjugate bases. But before I leave, let's label these. I'm probably mixing up my colors, but aromatic, anti-aromatic, and non-aromatic, because this molecule is big enough to become non-flat. Because if it stayed flat, it would actually be anti-aromatic. Okay, and in this video, we showed this stability trend. Last thing, cyclobutadiene cannot do the trick that cyclooctatetrene can do because it is too small. So we're going to say, and then I'll leave you to consider these points, is that rings, 5 atoms in the ring or less, consider them flat. We have to have a cutoff point. And experiment does say that once you get up to 6 atoms, the molecule will have enough flexibility to try to avoid being anti-aromatic. So this is a great rule because it seems like you should not have any anti-aromatic molecules that are bigger than 5 atoms. Because if that's the case, they could become non-flat by just puckering, just like the 8-membered ring did here. Right there, this one. Okay, I know that was a lot. Again, aromaticity is, again, a very tricky concept, not only to learn, but also to teach. For the rest of the videos, we're just going to do practice problems, okay? And look at reactivity and acidity and basicity.